which will be probably more easily to understand to you, and which is more related to what we actually did in the last maybe 5 to 10 years. And this is the experiments on these nanocrystalline thin wires. So some things which I said before will hopefully become more clear. But I would like to give you some overview of what is necessary to do this type of experiments. It doesn't mean it is a good idea to try to repeat them, but it's necessary for you to understand it, and maybe some part of that you can use in your experimentation. So how did we came to it? It was in something like 2005. Somehow we joined European project on development of textile processing with nitinol wires. So the idea was to transfer the functional properties of nitinol from a single wire filament to the textile. And so the first question was, can we obtain the enough, because you cannot use 1 millimeter thick bar in textile processing, so can we obtain and in textile processing they have very thin 1 to micrometer filaments, and this is very difficult to make from nitinol. It's possible from metal, but not really easy from nitinol. And so we approach the companies whether they can give us few kilometers of thin wire. They kind of they didn't have this possibility, but says, okay, if you ask for that, we can do it for you. But then the problem was they were not used to the spools which textile companies use. So we got the spools from the textile companies, gave it to the Fort Wayne Metals. They started to produce the like 20 micron to 50 to 100 micron. So we switched to 100 micron, but for textile processing, the 20 micron fibers became available in 20 kilometers on a single spool. This was the precondition that such kind of textile processing can even start. You know? But okay, so then we had the lots of nitinol thin filaments, and our goal, it was a European project with about 50 members, different industries, different universities, and we got a goal to develop the model of textile fabric with nitinol. It was prepared by Italians who were kind of like managers who were able to get this project, but didn't really care much about the content. So the goal for us to develop the models of thin nitinol filament, in fact, created the work for us until now. We are in 2023, and we don't understand even the behavior of the single wire. Yeah. So the idea that we will be able to have the models of textile based on the properties of the wires was stopped completely idealistic, and it could not be fulfilled. But the project went for 5 years. Something was achieved. Then we had our national project for another 4 years. So we have some patent for textiles, but we still don't understand the behavior of a single wire. So this is natural how these kind of activities proceed. This was in 15 years ago. Now very similar activities are in United States. They come with new and new proposition for nitinol textiles. But I will speak a little bit in my final talk about the textiles, but this is all about the nitinol wires, which is basically necessary to be able to develop the models. You have to understand the material behavior.
What is the application of these textiles?
Okay, so we have like The information is not so. I know what we are doing. Yeah. So we have one collaboration with a textile company who makes the stand graft. Stand graft is if you have stand. So around the stand there is some textile tube. Yeah. Even this textile tube can be made by combination of polymeric and nitinol wires. And if you make it from nitinol, it will keep this shape. You know, if you make it from polymer fibers, the tube will become flat. But this will keep this shape, which is very good in the body. So they can put it into the body, and the tube will automatically have this shape. You know? So this is called nitinol stand graft. And then we have some kind of like 3D, I will show you later on, 3D spacer fabric, which is made by nitinol wires, memory wires, and if you heat it, it will go to its shape, but it will just make it like that. So there are two layers which will be separated with the tubes in between. So for example, if you have a firefighter clothes, when he comes to hot temperature, this will be like separated and it will be isolating. No? So such, or we have the Velcro zipper from filaments, which if you close them together, something like you have for shows with polymeric fibers, you can have it also with metallic fiber. No, good. So we have the patent. No one is interested. Yeah, but nice application. Like it has a very big power. Like in normal polymeric, you cannot, even if you make big area, you cannot put 100 kilo. 20 micron filament. It was kind of strange to put it into the big instron testing machine. It can be done because it's long, but the experimentation is complicated. So we started to develop some small tensile testers with LabVIEW control system, which can perform loading, heating. So this is a copper environmental furnace, which is operated by Peltier elements inside. So it's covered, so you can perfectly control the temperature inside, and because the filament is thin, so it's pretty precise. It's all completely closed, so there is no wind, because if you have thin filament, any kind of wind blowing will completely change your stress strain characteristics. So, and because we did the X-ray, so there is some hole for X-ray beam over here. So now we have like 5 or 6 such kind of testers for different purposes. It's relatively cheap, and it can be used. And okay, we sold like 2 pieces. It takes us a long time to make it, and this is not really our work, but if there is interest, we can do that. You know? There is like 10 years experience in two things. And okay, and it has one advantage, and this is that we are, the grips are non-conductive, so we can measure the electric resistance, but we can also use it to perform the heat treatment by Joule heating. So if you put the wire into the furnace, you put it at typically 500 Celsius for 10 minutes. But if you do it next time, there is no like this is convenient in metallurgy, but with nitinol sometimes the process occurs already when you put the sample into the furnace, which is already preheated. Yeah. So when you are heating the wire, it occurs. So if you do it next time, you do it a little bit slower, and the wire is different. Yeah. So if you want to have exactly same wire with exactly same microstructure and exactly same properties, the heating in a furnace is not always ideal. So we have developed this kind of electro-pulse treatment, that we send a short electric power pulse into the wire. The temperature is not 500, but maybe 700, but only for very short time. So here, this is like the estimation of the temperature when we send this power pulse, and the Of course, this is the time for 8, 10, 20 milliseconds. So if we continue it, the temperature will increase and the wire will break. But when we stop at 20 milliseconds, the temperature goes down. So still it is exposed here to high temperature for some time, because the time you see it's very in milliseconds. So by adjusting this time, you perfectly control the maximum temperature which you reach. And the material microstructure is controlled by this maximum temperature which you reach in this experiment. So by this electropulse treatment, we can prepare a wire which have different microstructures depending on the pulse time. And we can also, because we are doing it by electric current, so we can measure, and it's in the testing system. So we take the wire, we fix the length, and then send the pulse. And when we send the pulse, we can observe the stress. So this is actually the situation we discussed yesterday. When you have the wire in Martensite state and fix the length and start to heat it, the stress goes up. Yeah? So the stress goes up here, but it goes up to some maximum, like 500 megapascal over here, and then it decreases to 0. And at the same time, we are measuring the electrical resistance. So at first when you are heating, nothing is happening, but then the resistivity goes down. So some process occurs here, which is related to the change of the electrical resistance of the wire. So we have some control what is happening during the heat treatment. There is a paper published, it is listed here, which analyzes what is happening during the heat treatment, but I will not go into the detail of that. This is just to demonstrate that, yeah?
Previous slide, why does the stress go up and come down? Like, why is it a peak?
No. Okay, so
yeah, like, so why is the peak there?
So what you are asking about this?
Stress going up and falling
Okay. Again, there are some physical processes. I will talk about them later. Now, if I should answer, so as I said, you have the wire. Wire is pre-straight and length is fixed. Yeah. So now there is martensite in it, and we are heating. When we are heating, martensite wants to shrink, so stress goes up. And if there is only this process, it will go up forever until it fractures. But in some moment, the martensite start to deform plastically. So when the martensite deforms plastically, the increase of the stress will stop. The wire is transformed to austenite, and then the thermal expansion occurs, and the stress goes down to 0. You know? And the fact that the martensite is transformed to austenite is evidenced by the decrease of the resistance. You know? Because the martensite has high resistance, austenite has lower resistance. In spite, you are heating the wire, and normally the resistance of metal will increase with increasing temperature. This occurs also, but the change due to the change of from austenite to martensite is higher. Yeah? So if I will show different.
So basically, this is a test to show that austenite is there in the wire, right?
Sorry?
It's a way to characterize austenite when the resistance.
Well, this is the way to heat treat the metal. Okay. Yeah, I am just showing the details of the method. That the beauty of this method is that if I have same kilometers of the martensitic wire on the same spool, now in 2023, if I do this heating and I use exactly the same power, I will get exactly the same wire with same microstructure, same properties. And there is a wide range of of microstructure, which I just show in the this is here. So when we look by electron microscopy, this is the cold work wire, and this is the maximum temperature wire with grain size few micron. Here it is like 1 micron with this, but we can go up to 6 micron about with 20 it's not linear, yeah. So if I make 20 millisecond here, it will be like 6 micron grain size. So these are completely different wires, very different. Yeah, you will obtain the same if you put them at 300, 400, 500, 600 temperatures. Yeah, into the furnace, you will obtain something similar if you put for something like 5 minutes. You know, no, not more. But there is some differences. For example, here, if you look into these grains, if you search for this location, you will hardly find one. So also, if you see these typically these kind of arcs over here, this is like the people who study the grain growth. They understand very well. This is how when the grain becomes bigger, it grows with such kind of such kind of shape of the grain boundaries. And because we heat and then we stop in some moment, so we are freezing this grain during the grain growth. We are freezing in some moment. You know? So here it's like 500. Here it is like 1 micron and 6 micron. So actually, and this all happens in millisecond time. So but with electric current you can make it precisely, very precise. It doesn't depend on time, on anything.
So we have corresponding microstructures also at higher magnification.
These are all austenitic microstructures. Well, what you will get with higher magnification. Here, if you try higher magnification, there is a lot of dislocations inside, yeah, because it's not recrystallized. This is semi-recrystallized. This is fully recrystallized.
I mean the optical microstructures.
These are TEM microstructures.
Can we have corresponding optical microstructures?
No. Well, how you can have? This is too small. It will be 1 point in optical microscope. Yeah, you cannot have it. You have to have it. I mean, if this is the problem with the nitinol. If you want to, you forget about the optical microscope with nitinol. You have to use transmission electron microscope. Even scanning electron microscope is not enough for this.
So is it useful for training also? We can train.
Oh, sure, very useful. Yeah, very useful. No. Okay, so this is the method how we prepare the wires, and then I will go quickly through some experiments. It's all summary, many tests. If you want to understand something, raise the hands because this is important to explain. You know? So first is that most of the people who do the research on nitinol wires, they simply do the test and stop here and unload and see the superelastic curve and discuss the property of the material based on the superelastic curve. But this is strange because this is not normal in material engineering. The other people who studied titanium or aluminium, they never deform only 5% and unload. They always deform till the end. And so one day I had a Chinese, nice, very good PhD student. So she quickly learned to operate this, and then, she was doing her PhD in China for maybe 2.5 years, but she was not very happy with what she did so far, and she came to Prague for 1 year as a part of her PhD study. So I discussed with her what we could do, and then we made some kind of agreement that she would study systematically tooth wires. So thanks to her, we for the first time we made the systematic analysis of nitinol wires and deformed cell till fracture. And she didn't know much about, she was more also from engineering, some vibration damping stuff in aerospace. So she came to it and she did excellent job. We published in about 3 papers about that, and these figures are from her work, from this, they are listed there. And so what we found is something like this, and you will find it on every nitinol, wire. So this is one at room temperature, and wires with different microstructure. Yeah? So the hard wire is elastic and breaks at about 2 gigapascal, as I already said. And then if you continue and the grain size become more and more big, you will obtain such pattern. So the most interesting wires are here about 10 or 12 milliseconds, which have the high yield stress for plasticity here, but they all fracture around 12 to 13. So if you if you buy somewhere a nitinol wire, it will fracture around here. So there will be no chance for you to deform it to 60%. But somewhere around here, the blue, 14 to 15, suddenly you will go up to 65%. Here will be like a plateau and then go down. But if you plot it in true stress, true strain, this plateau, like the cyan, for example, you see, becomes still hardening. Yeah? So in reality, there is still hardening, but there is this transition from low ductility to high ductility, which occurs somewhere between 14 and 15.
What is that 14 millisecond?
This is this millisecond. You can translate it to the grain size. Yeah, I think it's here. Yeah. We use this electric power pulse heat treatment, which is here, and this is translated to the grain size along this line. So here you will have grain size like 7. No, this is resistivity. This is grain size. So here you have the grain size related to, understand? Okay. So again, this is important that you understand. We heat the wire by electric current. So this is the electric power pulse. Yeah. So this is the maximum power, and this is the length of the power. Okay. The length is in millisecond, 2, 4, 6. Depending on the length of the power, you will have maximum temperature, because when after 20 milliseconds it switch off. So we reach the temperature like nearly 1000 degrees. But this is only calculated through heat equation. We cannot measure this temperature. Yeah? So it's so-called so estimate. And then if you look into the microstructure of different milliseconds, you will have different grain size. So if I show somewhere in a diagram millisecond, pulse time in millisecond, you can imagine the grain size. Here it will be 18 micron, here it will be few nanometers.
She did this work in 1 year?
What?
This much work volume she did in 1 year?
This she did, she's Chinese, she did it in 1 month. Very, very smart. But the whole technology was developed by many people. She only did the test. But okay, there was a change of. We also studied superelastic curve, but then we started to think about this plasticity, and then we said, hey, why we don't measure the test till fracture like everybody does?
Professor, like all these wires are treated in this inter-wire cluster.
Yeah.
So what used to be the length of the wire?
50. Okay. You know, we use. There is a problem. If you do be patient. Yeah. If you do thermomechanical experiment, you have to measure strain with high precision. To measure strain with high precision, you need a long wire. The longer wire, the better you measure the strain. So we started with 10, and then we made the furnace for 5 centimeters, and 5 centimeters. Mostly in the experiments we use 5 centimeters, but we have also the furnace. This depends on the length of the furnace. Yeah. So the length of the furnace we also have for 22.5 centimeters, 25 millimeters. Yeah. And the problem is in when we use, for example, the same wire in DMA, the maximum length is like 1 centimeter. If you have 1 centimeter length and you want to measure precisely the strain during thermomechanical cycling, you have to compensate all the changes of the grips. But in DMA machine you can do it. Yeah, you can use some quartz sample and you can estimate, you can calibrate it. But this is very, very. You have to do the calibration again and again. So it's time consuming and lots of work. So we prefer to make long wire. So we decided in this textile studies with 10, but then because of the furnace we shorted to 5 centimeters. So the 5 centimeters is the length of the wire.
It's not due to electric heating, right? It's due to the rapid, this furnaces?
Okay, if I talk about thermomechanical experiment, we cannot heat the wire by electric current, because if you have austenite and martensite, they have different resistance. So you would have different, and the deformation is localized. So half of the wire would be in martensite, half in the austenite. You will have different temperature because you have different resistance. So we never use the electric current to. If we want to make controlled temperature, we always use environmental control by this furnace, Peltier furnace. But it can be heated, cooled very quickly because the wire is thin. Peltier. It's Peltier element. It's a ceramics which you feed the current into it and it will become hot, and it can allow also for cooling. You can cool down to -50.
Time.
Millisecond applies for Joule heating, for electric heating. This applies, yeah. So the Joule heating is made to change the microstructure, to heat treat the material, just like if you put it into the furnace. And then I perform maybe heating, cooling under constant stress. This is also heating, but heating only to maybe 100 Celsius and cooling to -50. And for this, we use Peltier. We never use electric current because we cannot have active cooling. But with Peltier, we can control the decrease of the temperature in time to be linear with Peltier element. And this furnace, discuss some of the specific things in more detail, and this is this plateau length. So we published an article about the analysis of this plateau length, and the work was done by doing systematically the test only till the end of the plateau, like we normally do in the shape memory field. Yeah? So in the shape memory field, you are loading the wire to the end of the plateau, then unload, and if there is some unrecovered strain, we heat the wire up to 200 Celsius and unload. Yeah? So here, this is the maximum strain. This strain is the permanent, which could not be recovered by heating. This is the strain which was recovered by the heating. This is the strain which was recovered on unloading, and this is the elastic strain recovered on unloading. Is it clear? Yeah. So in this case, we can analyze the strains, and we look into the material by transmission electron microscopy. So if we did that, so at room temperature, which is somewhere the green curve. The green curve here, it's perfectly reversible. This is the green curve. So if we look into the microstructure after, you will find practically no dislocations, no damage. What? Okay. You can hear me, but you want to record it, isn't it? So at room temperature, the superelastic cycle no harm. Little few dislocation here and there, but at just slightly lower this is room temperature here. Almost all is recovered. At 50 degrees, it's still almost lots of recovered by on unloading. Before it was recovered on heating, now it's recovered on unloading. And if we look into the microstructure, we see some dislocations and some deformation bands like this. It is all in austenite because we do unloading and then heating, and the material is in austenite at room temperature. And when you look at it at austenite. At 100 Celsius, where the plateau strain becomes large, so there is still plateau. The plateau strain, you see it's almost 16%, very, very long. You don't see it normally, but if you go to high temperature, you will see it. And inside the microstructure, there is lots of deformation bands like this. So this is in here. And when you go even higher temperature, like 200, lots of dislocations, but not many deformation bands. And also, where it is? Okay, I discuss. So maybe I should explain now a little bit what we actually measure. So we observe this plateau. So if you take the wire and you measure it in tension, you will see that the stress remains constant. And this is because the deformation occurs in such kind of localized manner. So this is a sort of shear band which propagates during the wire upon loading and unloading. And this is a big complication because normally the material deforms in homogeneous matter, but nitinol deforms in this localized manner. And you have to somehow take this into consideration, and so if I say we have the plateau, this actually means that the strain which is localized inside this propagating band is 16% long. But we don't know whether it is only only transformation or some plastic strain. Yeah, so here it is mainly only transformation, but here it is partially plastic, and here it is mainly plastic. But still, without transformation, there would be no plateau. So it's not very clear what do we observe here. This is another method which we use to analyze this localized deformation. It's called, digital image correlation is normally used to visualize 2D strain on the sample. But because we have a long thin wire, so we have 1D digital image correlation, and in fact this is the length of the wire from it's 30 here it's 30 millimeter long, and this is the time. And now if you see the line like this, it's this band which propagates from this direction to here. The color is the strain. Yeah? So the strain changes from blue to red, so it's like a 7% strain, and it occurs in this time, in this position. Do you understand it? Not really. Who? I will use a lot these figures. So if the deformation is homogeneous, there will be gradual change, like from blue to red over here. Yeah? But because the deformation is localized, so this method, it's like we in camera we observe the wire, and from the change of the pattern on the surface we evaluate the strains, and so we have like a extensometer which evaluates in many points along the length of the wire the strains. Strains are the color here, and this is the motion of the interface during forward transformation, and this is the motion during the reverse transformation. And in this way we can find out whether the deformation of the wire is homogeneous or localized. And you have this problem every time with nitinol wire. So be careful about that, and the evidence is this plateau. If there is a plateau, there is always localized deformation. And the question is, what is this plateau length? So the plateau length here is like, this is in strain, so 7%, 10%, 15%, and 10%. So why it is so different? Okay.
When we stretch a nitinol wire, let's say to 4% or something, between the plateau region, and we stop it there, we unload it from that point.
Okay, so you stop it, for example here.
Yes.
So you have half of the wire in Martensite and half of the wire in austenite.
And we unload it, then after that again it will be back to austenite.
Yes, the half which is in Martensite will go back, but the other half will be intact. Yeah.
So, but in that equation, right, in that experiment, there's no heat treatment?
Every nitinol wire behaves like this, almost every. Heat treatment here, okay, this is just the schematical picture, yeah. But approximately heat treatment could be any of these heat treatments which we use, which give rise to superelasticity. Yeah, so it would look like that. So be aware of this localized, who doesn't know about it, be aware of this localized deformation. In the experiments you have to fight with it. So you imagine, for example, we want to look by X-rays into this point. So the X-rays are hitting the material in this point. So we see nothing, then bend is coming through, the change is from 0 to 6, and then again nothing. Yeah? So because of this localized deformation, we cannot follow continuously during straining. Yeah, so it's a complication for many, even for applications. Yeah? But it's reversible and it works, and we have to live with it. Yeah? But okay, the aim of this article was to explain why we have such kind of different so this TEM give us some clue. We have here suddenly around 100 Celsius, when the plateau length becomes long, there is a lot of dislocations which suggest some plasticity have occurred. It's clear. So this evidence suggests that plasticity did occur, but we need some systematic. So the Chinese girl did it on this is for different wires. So this is for 10 milliseconds, so very hard wire with very high yield stress. This is for 20 milliseconds. And you see it's the maximum at high temperature is everywhere, but here it is at 200 Celsius and here it is around 50 Celsius. So this phenomena with plasticity, the more you anneal the wire, the more you will have them. And it is the reason for having this maxima of plateau strain is that the martensite, which is created by loading, will at the same time deform plastically and create these deformation bands in the microstructure. So while it transforms, so inside this propagating band, if it is at high temperatures, around 50 degrees C, the martensite deforms plastically. Okay, but the problem is why it decreases with further increasing the temperature. Why there is this maximum? And this was explained by using in situ X-rays. So here, this is the strain maximum, and at the end over here we look into the material by X-rays, and you will find that at room temperature, which is here at room temperature, this is the evidence for martensite. So the band, the martensite, when it propagated here, so the microstructure in the martensite is fully martensitic. Yeah, it's fully martensitic. The volume fraction of martensite is 100% at room temperature. But starting from 50, when we look into the microstructure, it went down to, so now we have the problem that at high temperatures, around 100, at the end of the plateau, when it is long, which is like here, 100, we have mixture of austenite and martensite. This is austenite, but these peaks are martensite, so it's a mixture. There is this for volume fraction of martensite. At 100, where the long plateau is, we have at the end of the plateau half of the microstructure in austenite, half. So it's a kind of different. So the question is, why we have austenite at the end of the long plateau? Because intuitively, the more martensite, the longer is the plateau. But no, we have less martensite and longer plateau. And we have these deformation bands in the microstructure. So we had to explain this. And you mean here? Yeah.
Middle graph,
Yeah. This means that even at temperature 150, we still have some martensite peak. Okay. That's a complex question. This is stress induced in all cases. In all cases, this is measured under stress, by diffraction under stress. We have this machine, we keep the wire under stress and measure the diffraction. But it has something to do with the deformation mechanism during the loading at high temperatures. So I will come to it later on. But no.
In case of 2% or 4% strain, we are getting a completely reverse transformation, right? austenite to martensite, and there is no dislocation forming. So
Yes.
Why it is not following the same path, same deformation path? So why it is forming a hysteresis?
Okay, what you said is the green. At room temperature, it's perfectly recovering. But now around magenta, which is like 50 degrees, there is still plateau, but on the reverse, not everything, which suggests that something must have happened during the loading or unloading. Probably during both, but as a result of this, you have non-recovered. And even if we heat it, we could recover only 0.5%, but still 2.5% remained. Yeah. So somewhere during this loading, the plastic deformation was created, and we try to find out when it happened and how it happened.
So my question is, when we are moving from 0% to say 2%, and then we come back again to 0%, we are performing a complete cycle without involving heat. So if there is no change in the material before and after the deformation, why we are getting hysteresis?
Okay, first time to forget about this curve. So if you start to unload here, I need to wait, but it's not a good idea to talk now about partial loading, because if I stop here and unload, so it will go down back, but inside the material the strain was 6%. So you apply 2%, but because of the propagating band, in some part of the material was deformed up to 6%. So you don't have partial cycle, in fact, much. You will have the same phenomenon. It is clear. This is the consequence of this localized deformation.
Sir, I think I'm not able to.
Yeah.
Suppose that in this case we are moving from this 0% strain, we are going to till end, and there is a complete transformation of austenite to martensite.
Yes.
And then we are on the reverse cycle. Basically, after the end of each cycle, we are getting to the initial position, right?
Yes.
So why we are getting the hysteresis when there is no change in the microstructure? After one complete cycle, there are
No. There is always no. If there is a Martensitic transformation, there is always hysteresis. Yeah. So this has nothing to do with this plastic deformation. The only if there is plastic deformation, here some plastic deformation is over, the hysteresis is wider, but the hysteresis is here always. Hysteresis is here because of Martensitic transformation. Even if it is completely reversible, you have hysteresis. Why you think there is no hysteresis? Even with complete reversibility, you have hysteresis.
I think his question is why there is a hysteresis.
Why there is a hysteresis? This I was talking yesterday about it. If the Martensitic transformation is a diffusionless solid state transformation due to nucleation and motion of the interfaces, and some people add with hysteresis. Hysteresis is attribute of the Martensitic transformation, and why it is here is because maybe by loading you supply energy, and some part of this energy is dissipated into the heat, latent heat. But latent heat is compensated on cooling, but also is dissipated into the defects which are created, which possibly are. You hear a sound, so there are elastic waves, and all this energy is lost. And if you have some lost energy, you have hysteresis. This occurs during forward and during loading. During both transformations, some part of the energy is lost, and if you take the area of this hysteresis, you can convert it to the dissipated energy by thermodynamics approaches, and you can calculate that. But for your question, why there is a hysteresis, this is very basic question. I only can answer. It is here always because energy is dissipated during the Martensitic transformation. You have other type. During elastic deformation, no energy is dissipated, so you have, even if you have nonlinear elasticity, you would have the behavior like that, because the energy is not dissipated. But here, because this elasticity It's not true. It's not Hooke elasticity, but elasticity due to this finite straight gradient and motion of the interfaces. Probably the motion of interfaces is associated with the energy dissipation. This is what most of the people believe in. Yeah, there are big energetical framework developed on it, and in fact, understanding how the energy is dissipated, you can develop a good thermomechanical model of SMA materials. So it's very interesting, but like my talk is not about it. Yeah, no, but it's a very good question. Yeah? Understanding the you clearly understand that in this case only small amount of energy is dissipated, so the area is small. But in this case, this and probably you don't have even the end. So much more energy is dissipated if you do stress-induced transformation at high temperature. And then you may ask why. Why is that? And we would have to explain why more energy is dissipated. Now, because there is a lot of other processes which accompany the Martensitic transformation at high temperature.
I don't know whether this question is relevant, but can I compare always the reverse Martensitic, the reverse transformation happens at lower stress. So can I compare this one with the undercooling during solidification?
Yeah, you can some sort you can no in
melting. I mean solidification doesn't happen at melting point, but it is really lower than the solidification.
You have here this peak. So you are loading, and then there is a drop. Why this is here? This is because this now the bend is formed. There is a jump. So this jump, in reality, if you look on the surface, it could happen in the middle of the wire, and suddenly you have like a thin band which appears in the middle. So there is a nucleation which is necessary for that. So you need some overstressing, or if you do cooling heating, you need undercooling to nucleate the band. Once you nucleate the band, it propagates at constant stress. So you are perfectly right that the hysteresis is connected with undercooling and overheating, but it is not the physical origin of it. It only somehow modifies it. The physical origin is the dissipation of the energy.
All of these plots that are shown over here are not having information about the strain rate. So is there any relationship with strain rate and this formation of this effects which result in this?
No. This is also very frequent question in strain rate. So my opinion is, based on my experience, that the superelastic deformation is rate insensitive. The only problem is this latent heat. So because you have the latent heat, if you do it quickly, the latent heat cannot go out of the specimen, the temperature increases. So this is because of thermomechanical coupling with the environment. If I put some stream of very cold air, it will be almost adiabatic, and then the stress strain curve would be very similar in the range of very different strain rates. Yeah. So in the first approximation, the strain rate is strain rate insensitive. And if you imagine, like we use frequently, the people who develop the actuators, they put constant force and cool and heat the wire. Yeah. So if you are cooling under the constant force, you are cooling with some rate, but you don't control the rate of the transformation. And then the suddenly the transformation starts and increases and proceeds extremely quickly. So we are doing the experiments in which we do not control the rate, the strain rate. And okay, in engineering, if you have the strain rate depending deformation processes, this would be a criminal act. You cannot do that. You have to control the constant strain, but we don't care in shape memory field. So this is some indirect confirmation that in the first approximation it is rate insensitive. So because we don't care about it, we keep it constant always, something like 2 to 10 to minus 3, quite fast. Yeah. So in other, if you normally we use like 2 to 10 to minus 4, and this is like 10 times faster. But well, sorry, again.
Yeah, in the case of rate dependent thing, so total transformation of Martensitic will not happen.
No, well, I said that this is rate independent. This is not rate independent. Once you have the plastic deformation inside, there is no guarantee that it is rate independent. And the problem is, like, if we did the experiments also at, let's now shift it. No, but okay. I just to answer the first question at first there. So the loading when the Martensitic transformation occurs is rate insensitive. But if you do it at high temperature, 200 or 300 Celsius, it's rate sensitive. So it depends whether you do it in load control or strain control. In strain control, the response would be like that. In load control, it would be like this. Yeah? So one has to be very careful, but only at the high temperatures or in very soft materials, fully annealed. Then you will get the rate dependency. And your question was?
Yeah, so in the general models, we are considering that the inelastic deformations in the shape memory. So what would happen if I am considering like a visco inelastic? Then I have to consider as a rate dependent.
Well,
that the transformation which we are doing is the inelastic deformation.
Okay, viscoelastic deformation would imply creep, yeah. And so far I know if you keep the constant stress in this range where only Martensitic transformation occurs, nothing will happen. You stop the test and you come 5 weeks later and it will stay at the constant. There will be little, yeah. So there is no creep in case of Martensitic transformation only. Once you go to 150 Celsius, there is some creep, but it's not a viscoelasticity due to the rate dependence, not due to the time dependence. You know? So you have, when you stop, but the process still slowly continues like a relaxation, and you will get some phenomena. Okay, I need to continue. So this is very important. So we see the plateau, but the plateau never means that all your sample transforms to Martensite. At high temperatures, you have only 10% at the end of the plateau. I didn't say what does it mean, but just a warning for you. If you see the plateau end doesn't mean 100% Martensite. So if this curve, like the over here, where the volume fraction is maybe 20%, so if you continue, this phase transformation will continue upon further loading because you have lots of austenite in the wire. Yeah. Okay. Now, so this is some, again, because it becomes important. Yeah. So if we cycle the wire at room temperature, only small dislocation loops here and there, but nothing significant. Around room temperature, deformation bands, 100 temperature, lots of bands. At very high temperature, mainly dislocations. I will probably, this is the evidence for residual martensite. So in some bands we can identify the residual martensite in the wire at 100 Celsius, but it's not so important. Okay, so now I should explain why we have this plasticity, because we don't have really many dislocation. We didn't see at 100 temperatures. We have seen mainly these deformation bands inside. So we came with some kind of explanation which recently it was in line with the literature evidence, and this is that inside these deformation bands, the austenite lattice which is there is not the equally oriented as it was before, but it is rotated. So the deformation bands is in fact rotated austenite lattice. It's one, because it's 1-1-4 twin. There is exact orientation, so we call it austenite twin. But for us now, it's important that after the deformation, I have an austenite lattice which is rotated. So we believe that this plastic strain is because of the rotation of the martensite lattice. So the question is how it happened, and well, this can happen, yeah, because if you imagine I have austenite, then it is elongated here, then I rotate the lattice, and then it's even more elongated, and by these rotations I can induce up to 50% strain. So the question is that like if we are supposed to have the shape memory phenomena, so here in the martensite the misorientations must be always such that they return the austenite to the original position. If they return to the rotated lattice, we are in trouble. So this is like in free energy terms, it can be confirmed by this diagram where this is the austenite and this is the martensite, and there are two wells, so there are two Marians for two differently oriented martensites. And so when the temperature or energy is changing, you are changing the position of this minima. So if minimum of martensite is lower, it goes to the martensite. And now when you are in martensite, if you perform such twinning that the martensite lattice would be oriented in such a way that when it goes back to the austenite, it will create the austenite which is rotated. You manage this sort of plastic deformation. So you see, this is also austenite but differently oriented. Okay, so like here you have some kind of boundary where if you perform some kind of twinning from this well to this well, you are actually getting more closer to the orientation of different orientation of austenite. I don't want much to go to the details of this, but one can imagine that so during the straining, this is austenite, you go to the martensite which is here, then this martensite can twin to the green which is here, and then the green can go to this, and you are back to the austenite. So now I have actually a scheme when upon straining I will get transformation from austenite to martensite to austenite. So we call it B2 to B19 prime to B2 twin. And now this explains that at the end of the plateau I will have austenite. Yeah, so you remember there was this moving band, so inside the band there is a martensitic transformation to martensite, but even going next to the austenite, and so no wonder if I look on it by X-rays at the end I would see mainly the austenite. So this is some scheme which we provided. it's correct, but it occurs slightly different way, and I will talk about this tomorrow probably. Yeah. So take this like a qualitative explanation. It can be used, but I have to say a little bit more details. This is basically the same which I said. So just the main thing to remember is that the plateau strain is definitely not constant. It can change at high temperatures around 100 degrees. It can increase, but the increase is due to this twinning mechanism, which is related to this reorientation of the austenite lattice underneath. And at still higher temperature, you don't have it. So if you don't have it, you have a lot of slip. So the reason for this decrease is that this process of twinning is not so active, and you have normal twinning in martensite or austenite, we don't know, but as a result the plateau length is short. The reason why it is here long, the plateau, I forgot to say, is you can imagine here okay, this is at room temperature and this is at 100 temperature. Yeah? So this yellow, it gives maximum something like 11%. But here now I have this twinning in martensite, and the green provides larger strain. So if I have composite of yellow and green, where green provides more strain than the yellow, I get a longer strain here. So this is the explanation why we have here the maximum. And at high temperatures, this problem disappears because we don't have this twinning in the martensite, and then the plateau will slowly disappear. Okay, good. And so with this we understood the unusual increase of the length of the plateau. But then there was a question about how the wire differs further up to the fracture, because some of the wires fractured at 13%, but some wires deform up to 50%. So we made similar experiments. Again, the Chinese girl did it. We agreed on 3 sets of experiments. So this was the third one, where we loaded up to some maximum strain, unloaded, heated. So an experiment was up to 20, 30, 50. So in this way, we check the unrecovered strain and we look into the microstructure. Similar figures look like this, but the one for me very important information is that this is loading at lowest temperature, like minus 90 degrees, and so you see again the same type of strain. So this is permanent strain, and this is the heat. Blue is heat recovered by the heating and unloading. So if you look on it, you have here around 16, 10 to around 16%. You have maximum recoverable strain. This red is unrecoverable. Red is permanent. But even if you load the wire up to 20, 30, 40, you still have 10% recoverable strain. So this is somehow, I am not sure if like, I was not aware about that, but the wire deforms plastically, but still the recoverable strain, which is on unloading plus on heating, remains still 10%. This is something which is very difficult to understand, because if the deformation occurs by plastic deformation, this should not really happen. The question will be why this 10% remains. So it is the case for low temperatures, but it is not really the case for very high temperatures like 150. We have most of the strains are permanent, not recoverable. So when the cubic to monoclinic transformation occurs during loading, you have this type of recoverability of strains. Mm?
Previous cycle. So this is for the initial cycle or the stabilized cycle?
This is first initial, this is one cycle on each wire. We heat treat and deform and destroy.
Very first cycle.
Very first cycle, first cycle, yeah.
During the plasticity, the temperature is also increasing.
Well, we don't, no. The temperature is constant during the temperature. Okay, during loading, the temperature is constant, and then we, at small applied stress, we heat it to get rid of the martensite. Base goes up, and there is no more. This is fully austenite, and if you cool down to room temperature, it's austenitic, and we can look on it in the TEM. Notice somebody asked me yesterday. This is related. I'm not sure if I have it here. Okay. I don't really have it here, but if you we deformed up to different maximum strains. So if you deform up to 16%, then in the wire you will find the microstructure like this, or even better like this. So these are the bands where the austenite lattice is differently oriented, and this is the confirmation from the TEM analysis. The red is the matrix, and this blue and green are these bands in the twins. So if we perform, it's called dark field analysis. So when we visualize this grain with the diffraction from the particularly oriented austenite, this is the blue twin, this is the green twin. So we see only the twin lattice which is oriented these are the diffraction spots in which we did it. So if you did it with these diffraction spots, you would see the lattice which is oriented, and this is arranged in two bands. If you take the green one, you will see this lattice. If you take the red one, which is from the matrix, the bright would be only the matrix. It is clear? So with that, we can understand how the austenite is oriented within this grain. And we see that the red is the original parent austenite, and blue and green are these kind of misoriented matrices. So if you have such kind of microstructure in the grain, then, and I have it somewhere maybe a little bit down. Okay. No, it's not here. It's different. I will show it differently. But okay, if we look more in detail into this microstructure, you will find between these bands there is a lot of internal stress. So the austenite is not austenite, but there is stress, internal stress, and this internal stress is oriented. So when you cool the wire which has been deformed to 16% strain, there is this internal stress which causes two-way shape memory effect. But if you deform more, you will have much more of these bands, and the effect is no more. If you deform less, you will have no bands. So that's the explanation why you have to deform to 15 to 17% somewhere, depending on. And so the most we did it, we analyzed it systematically. So the most effective way is to deform it somewhere to about 16% somewhere here, and then it has a two-way memory effect. Okay, And probably the most important thing is this figure, which shows the microstructure in the wire at pre-order test. Pre-order test, then 10%, which is somewhere beyond the plateau, then 12%, 14%. So this is the ideal microstructure, somewhere between 14 and 20, and then 40 and 53. But you see, after 40% of deformation, if this is like 1 micron, so the microstructure becomes same like copper after severe plastic deformation. It's refined into the domains which are of 5 to 10 nanometer size. So such kind of microstructure, the material is extremely hard after such deformation, and it is almost like after the cold work. So if you deform the nitinol wire in tension, the mechanism of deformation makes it to be refined into the small misoriented blocks, which is the same which occurs during the severe plastic processing. But here it is caused by the deformation mechanism itself. So the deformation mechanism, because it rotates the lattice, because it rotates to lattice, and so like here we can still analyze it, as I will show tomorrow. But here it becomes so dense that even in conventional electron microscopy you can hardly analyze this, but you clearly see, and this process occurs at stresses like 1 gigapascal. So you can deform the material at 1 gigapascal and refine it into such, and up to the 50%. This is like no trip steel can do that. So the mechanism is not the same like in trip steel. It's a different kind of mechanism, but have the similar features. You can apply very high stress, very high strains, and finally you get a microstructure which is almost amorphized. So this was our first, but this is all in austenite. And so you may ask, what are the microstructures in the wire when it deforms? Because when it deforms, it is in martensite. It is not in austenite. So, but these experiments cannot answer it. Here we look only on the microstructure which remains after unloading and heating. So we have the evidence. This is some kind of relics on the process, but we don't really know what was there before. Okay, so this is again, as I said, and at every talk there is some kind of takeaway, where I try to formulate the most important things from each talk. So here I am at the end.